Dear colleagues, I am grateful that I can contribute to the SCIX conference at least in this way. The topic of my presentation is challenges in the laser ablation of soft tissues, which is quite a prominent topic in the laser-induced breakdown spectroscopy community. In my presentation, I will go through the basics of LIBS bioimaging. I will mention also challenges and limitations of the LIBS technology. And then I will cover the major part of my presentation, which is the optimization of laser-matter interaction and laser ablation of soft tissues. And then I will also briefly discuss the implementation of chemometrics and also the utilization of LIBS in cancer research. LIBS technology has already been used in many bioapplications. As you can see in the selection of review articles in the bottom, our publication about the implementation of LIBS in plant bioimaging, and also 2 other publications covering broader range of topics, including hard and soft tissues. Successful implementation of LIBS technology to the cancer research or the analysis of cancerous tissues still demands further work and is facing many challenges. On one side, analytical challenges where real-time response in data processing, accurate estimation of tumor margins is really necessary. This is a crucial part of the whole process and has to be solved. The correlation of histological images with other analytical techniques and also with the LIBS elemental maps is very important as well. And then the causalities that are beyond actually the biological processes and are connected to chemical changes in soft tissues. This is another key part of the research. On the other hand, instrumental challenges, there are so many of them, and the main one, I believe, is the sensitivity in detection of trace metals, considering zinc, copper, iron, and so on. This is a point where LIBS is really beyond other analytical techniques. On the other hand, throughput of the technique is quite good at the moment, but still may be considerably improved, and this is the main benefit of LIBS as such. High resolution, this is another thing that we really need to work on, and the biological standards or biological relevance is in the range of microns. And finally, the sample preparation is part of quite active discussions in the community, how really properly prepare the sample prior LIBS analysis. For our analysis, we have used several samples from mouse kidneys to human skin biopsies. One of them we obtained from Czech Academy of Sciences, the other from University Hospital. Both kind of samples were prepared in the way of formaldehyde fixing and paraffin embedding, and the mouse kidneys we used mainly for optimization because human skin biopsies are quite unique samples and we did not want to destroy them for some optimization. So the optimization was done on mouse kidneys, and we used 2 equivalent ways. One was to really compare the intensity of zinc signal, which was artificially administered to the sample in the form of drop of a solution. The other way was only simply to look for the potassium intensity in the kidney. This we would like to advocate by the ICP-OES analysis, where you can see that the content of potassium, sodium, and magnesium, for instance, is quite stable regardless of the size of the sample. So we can intra-compare measurements from different kidneys from different mice. That's quite interesting and important. For the analysis, we have used LIBS Discovery, which was developed at CEITEC BUT University of Technology. It's quite fine piece of instrument, and it's using Quantel CFR Ultra is a laser source, and detection unit consists of Cherry-Turner spectrometer and a CMOS detector, both from Andor. You can see the optimized parameters, and I will speak about them later on. First of all, we estimated the stability of our LIBS system to see how it fluctuates through the time. In both cases, thin sections and paraffin blocks, zinc and potassium intensity, we studied the difference in signal-to-noise ratio, and we measured very similar samples in the span of 1 or 2 months. In both cases, you can see that the stability is quite satisfactory, and we can then support the idea of comparing different results measured in different time. Another parameter, is actually a very important one, is the energy in laser tissue interaction. Again, on left side is thin section, on the other is paraffin block. In both cases, you can see that there is quite nice trend in the signal-to-noise ratio as a function of the energy, and it's rising to a certain point around 20 millijoule, and then it levels off and starts to be saturated. So the optimal energy, what we found, is around 15 to 20 millijoule. For the case of paraffin block, we also estimated the crater depth, which doesn't have such a nice trend, and there is actually further investigation needed. Other parameters that we have investigated are defocus and gate delay. In the left, you can see that the defocus was studied in few hundred of microns, and with increasing from left to right, the focus was getting under the sample surface. So you can see that you nearly need to go significantly below the sample surface to have increased signal-to-noise ratio. That it's very interesting phenomenon and needs also further investigation, because you are, in case of thin sections, getting quite below the sample surface, which has only 10 microns. On the right side, you have gate delay, and also, of course, the plasma is quite short in its temporal evolution, so 500 nanoseconds seems as a reasonable gate delay to achieve the best signal-to-noise ratio. In both cases, I'm just showing thin sections, just for brevity. For paraffin blocks, the results are very similar. Final parameter that we have investigated is the atmosphere surrounding the sample. I'm just showing again results for thin sections and the zinc droplet or the zinc signal, the signal-to-noise ratio of zinc. We have studied purge and atmosphere as such, so the best results that we have obtained are for argon purge and the sample in ambient air. That is quite interesting when comparing to just analysis in pure argon atmosphere without any purge, without any flow over the sample surface. So the best signal-to-noise ratio is for simple argon purging. So far we were just analyzing murine kidneys, and we were able to optimize the system accordingly. So we were analyzing thin sections and paraffin blocks, and now we can move to something much more interesting, to the analysis of Haemangioma. Haemangioma is only, or luckily, benign tumor, so this is only to see the performance of LIBS. You can see the comparison, and you can see also that the paraffin block is much better for the analysis as such. I'm just showing calcium intensity or map of calcium and its relative distribution. So when we move further in the analysis of Haemangioma, this is quite interesting human sample. You can see that we can also analyze other elements, calcium, magnesium, sodium, and all of them have quite different distribution, which then needs to be related to the histological image after hematoxylin analyzing staining that is on the left, and those results give us quite interesting insight beyond classical optical microscopy. So if you have simple analysis, such as the mapping of some soft tissue, then you can get some nice insight, but you can still move further with some implementation of chemometrics such as self-organizing maps, and you can see the image of mouse kidney, then the map of potassium, and finally some clustering. So you can see that LIBS data can reveal some differences in the sample, and this might be also helpful in the cancer research. So in my presentation, I have shown you two equivalent optimization protocols that might be used for some brief system performance improvement. And also I have shown the potential of the analysis of human cutaneous cancers, actually LIBS elemental maps. This is for further work. We also still need to do some improvements in instrumentation and data processing. With this, I would like to thank you for your attention, and I'm just showing my co-authors and funding.